Hey there, everyone. Here we are at the start of week 2 of online learning. So I hope you're doing well. Hope you're kind of adjusting to the new rhythm. Me trying to get up these content videos on Mondays and Wednesdays so that you can watch them in anticipation of our live Tuesday, Thursday sessions where I work through examples. Please let me know if you have any feedback. I'm very open to making adjustments as I need to. We're all figuring this out together, but I'm glad to have you along for the ride, and I'm very glad that I've had some feedback that you're adjusting to this rhythm. But please let me know if there's anything else I can do. But with that, let's jump right in and get going with today's new content.
We are continuing with chapter 13 today. So, if you remember, last week we spent a lot of time developing the sampling distribution for the sample proportion. And we specifically looked at when the normal model is applicable. So, we are continuing along that line, but what we are going to shift our focus to today is what we are able to learn about the population proportion from the sample proportion. So, in general, we want to understand what is happening in a population of interest. Perhaps we want to know what proportion of all TCU students graduated high school in a different state. Or perhaps we want to know what proportion of residents in Fort Worth actually work outside of the city limits. There's a well-defined population. We want to know something about a proportion in that population, but the best we can do is take a sample from the population and get the sample proportion. Now, in a perfect world, we can quantify the difference between the sample proportion and the population proportion by looking at the standard deviation. And remember, our formula for the standard deviation is given by the square root of P times Q over N. But in general, this requires knowledge of the population proportion. So we get into the circular reasoning because since P is unknown, we can't calculate the standard deviation either. However, if we know the value of the sample proportion, and remember we call this P hat, then we're able to calculate the standard error. And the standard error is our best approximation for the standard deviation. So our standard error is given by the square root of P hat times Q hat over N. And remember, the Q value is always 1 minus the corresponding P value. So the standard error helps us understand how far we generally expect the population proportion to be from the sample proportion. It's a measure of how much these quantities differ typically when the normal model holds. So let's look at an example of that. Let's say we want to determine what proportion of all births that take place in the US are premature. So our population is all the babies born in the US in a given year. However, that information is unavailable to us, but perhaps we're able to take a random sample, ensuring that the people included in the sample are independent of one another. We observe information for 100 different births, and we find that 14 of those were premature. Based on this information, our sample proportion is 14 of the 100, so 0.14. Of course, we could also express that as 14%. And because we're heading towards calculating the standard error, it's helpful to already calculate Q hat, which is just 1 minus the p hat value. So in this case, 0.86. Now, if we know that the sampling distribution is approximately normal, you can go and review the previous lecture for the conditions that ensure approximate normality is reasonable. If we know that to be true, then we can construct something called a confidence interval. Informally, a confidence interval is a collection of plausible values for the parameter of interest with a certain level of confidence. So we'll dig into this formula a little more in a minute, but for now, I'm just going to jump right in and calculate a confidence interval with a 95% level of confidence. Now, this requires that I calculate my standard error, which in this example is p hat times q hat divided by n, square root of that entire quantity, which ends up being 0.035. So my 95% confidence interval is then defined as my p hat value plus or minus 2 times my standard error, which in this case is 3.5%. So if I do that multiplication, that means 14% plus or minus 7%. That 7%, that quantifies how much uncertainty we have in each direction. So 14 minus 7 means the lower end of my confidence interval is 7%, and then 14 plus 7 means the upper endpoint is 21%. So my 95% confidence interval ranges from 7% to 21%. And that level of confidence, the 95%, we also refer to that as the degree of confidence. So that is a number that tells us how confident we are that the population parameter, or the population proportion in this case, is inside the confidence interval range that we have constructed. Now, I know a lot of you at this point may be asking, where exactly did this formula come from? How did I know to do that calculation? Let's see where I found that. And we have to take a lateral step first to make that determination. We want to look for a moment at something called a critical value. So when we are constructing confidence intervals, we need to specify a confidence level. In my example, the 95% was the confidence level. And then we can use the normal model and find a z-score as a reference value. So that z-score, that's my reference value. We also call that a critical value. And the critical value is a number that gets multiplied by the standard error. We denote it by z with a superscript star, and we find that using the normal table. So let's say that you want to construct a C% confidence interval. If you want to use your normal table, then the value inside of the table that you look up is 0.5 plus C divided by 200. How does this work? Well, we just looked at a 95% confidence interval, right? So if C is 95, that means I'm going to do 0.5 plus 95 over 200. And if I calculate that, I end up with the value 0.975. So if you look at your normal table, remember you have a row and a column that tells you what the z values are. You want to go and find inside the table the value 0.975 and see what row and what column that corresponds to, because that is how we find the z value. So the row entry and the column entry, if you plus those together, that will give you the Z star. And we'll do some examples of this in our live session tomorrow. Now, that being said, it is helpful to just go and memorize 3 important critical values. Whenever you see a problem asking for a 90% confidence interval, the critical value will be 1.64. Whenever you see something asking for a 95% confidence interval, the critical value technically is 1.96, but that's really close to 2. So if you look back at the example, we did a 95% confidence interval, and I used 2 times the standard error. That's a good enough approximation. And finally, if we want to do a 99% confidence interval, then your critical value is 2.58. So you find a critical value, and then there is a formula for the confidence interval. The general confidence interval formula is p hat plus or minus Z star multiplied by the standard error. The standard error is an estimate of the standard deviation, right? So our standard deviation is estimated by the standard error, which I'll just write the formula down one more time, is given by p hat times q hat over n, square root of that entire quantity. So we need to know our sample proportion p hat, we need to know our standard error, and based on the confidence level, the C% that we specify, we need to find a specific critical value Z star. That Z star, that determines how big our confidence interval is. And the bigger our confidence interval, the more likely it is to capture the true parameter of interest. And remember, in this case, our true parameter is P, the population proportion. So what we are saying by constructing a confidence interval, when we calculate this quantity, P hat plus or minus the Z star times the standard error, that gives us a whole range of values, and we have a certain level of confidence or a certain degree of confidence that the true value is inside that range. Now, this is worth spending just a few minutes digging a little deeper. What can we say and what can we not say about the population proportion P when we use a sample? In the illustration that we started with, we said in a sample of 100, we found that 14% of babies were born premature. So what does this sample quantity tell us about the population? Well, the first thing that would be very wrong to say is that because the sample proportion is 14%, that means 14% of all babies are born premature. No, samples vary. If someone else were to go and sample a different 100 births, they would find another number different from 14%. So the sample value is never going to be equal to the population value exactly. Anytime you take a different sample, you are going to get a slightly different number. So we can't just take the sample proportion and say that is exactly equal to the population proportion. We even have to be careful. We cannot say that it's even probably true, because that 14% is going to deviate to some extent from the population quantity. So it's not probably true that 14% of all babies are born premature. No, that 14% is close to, but not exactly equal to the truth. So in my third statement here, you'll see here 2 times the standard error. So this is a 95% confidence interval that's being constructed. Do we then know that the true value is exactly inside that interval? So from 7% to 21%. Again, no. It's not guaranteed to be inside that interval. We're 95% confident that it is, but 95% confidence is not being 100% confident. So these are all wrong ways of interpreting the confidence interval. Let's look at the right way to interpret the confidence interval. What can we say if we're using a sample? Here's one way of looking at it. We don't know exactly what proportion of babies are born prematurely, but our interval from 7% to 21% probably contains the true proportion. This word probably here is very important because that signals that we acknowledge there's some uncertainty. This statement is much better than any of the previous examples because it does two things. It recognizes that we need an interval of values to try and capture the truth, but it also recognizes that even that interval is not necessarily going to contain the truth. We are pretty sure that it contains the truth, but we are not going to guarantee that it contains the truth. That is just what statistics allows us to do. If we want to state this in a much more formal way, the best and most formal way of stating this is we are 95% confident that between 7% and 21% of babies born in 1998 were premature. So we're giving the range of values, we're giving the confidence interval, and we are saying how confident we are with that range of values. So when we do some examples in our live Zoom session, we'll really spend a little bit of time also talking about interpreting that confidence interval. Now, we are later on in this class going to look at other confidence intervals. So I think it's worth remembering that what we're doing at the moment, we talk about as a one proportion or a single proportion Z interval. The word one or the word single indicates to us that we're studying a single survey question. Was this baby born prematurely? Or does this person work outside of Fort Worth city limits? Like there's a yes/no question, and we are studying what proportion of individuals in the sample answered yes. We're also working with a proportion, right? How many yeses versus how many no's expressed as a proportion or as a percentage. And finally, the word Z interval signals to us we're making use of the approximate normal sampling distribution of the sample proportion. So when we put all of this together, there are 4 steps to calculating a confidence interval. You first have to find the sample proportion p hat. So this means in your sample, look at the number of successes or the number of individuals that satisfy a specific criterion and express that as a fraction of the total. So number of successes divided by sample size. Then we have to calculate the standard error, and I've written that formula down a few times today already. Our third step is finding the appropriate critical value, the Z star. And that makes use of the normal table. But remember, you can memorize those critical values for 90%, 95%, and 99%. Once we have these 3 quantities, then our confidence interval formula is p hat plus or minus Z star times the standard error. So I have one example to wrap up with today. I'm not going to delve into these calculations too deeply, but let's just take a quick look here. Let's say we take a random sample of 250 people who live in Fort Worth. We are interested in knowing what the true proportion is of Fort Worth residents who work outside the city limits. In our sample, we find that holds for 35 people. So sorry, correction here. This should be 200 Fort Worth residents. So when we express that as a proportion, we take 35 divided by 200. That is 17.5%. We calculate our standard error. That's the p hat value times the q hat value divided by sample size, and take square root of that entire quantity. This gives us 2.7%. So we have p hat, we have our standard error. We want 90% confidence, and remember the corresponding z star value for that is 1.64. So if I plug all of that into my confidence interval formula, I get an interval that ranges from roughly 13% to roughly 22%. So does that mean that the true proportion of Fort Worth residents who work outside city limits is between 13% and 22%? No. We are 90% confident that that's the case, but there's 10% that hasn't been accounted for. So we feel pretty good that the truth may be inside that range, inside our confidence interval, but we know that it may not be, and we know what the percentage confidence is on either side. So we'll dig in, do a few more examples tomorrow, and I hope all of you are doing well.